Hello all, I am Narendra Babu, research scholar under Professor Narayan Prasad Padi, IIT Roorkee. I work as SRF in the UAssist project. As a part of a student webinar, I will be presenting my research work which falls into theme 4 and theme 8 of UAssist project. This is the topic of discussion for today's webinar, that is harmonic instability assessment and resonance investigation of power-electrolyzed power system. This is a brief presentation outline. First, we will understand harmonic instability and resonance in a microgrid perspective because these phenomena are also observed in HVDC systems, PV, wind farms, and train traction networks. Only difference is that the frequency of occurrence as well as the source that create these two phenomena. After understanding them, a case study will be presented where low frequency interactions between inverter and grid will be analyzed. Here only the outcomes that we have derived from the analysis will be presented, which will be validated with simulation models, basically the average model, and later they will be validated using experimental results. Lastly, a short presentation on future work will also be covered. Now, let us understand these two phenomena. For that, a grid-tied inverter operating in current control mode is considered, as shown in figure 1. Notice that current through inductor L1 is controlled here. Some simple assumptions are made here to understand the concepts theoretically. As I said, since current through L1 is controlled and we are not controlling any of the variables after L1, that is voltage across the capacitor or the current through the inductor L2, we can assume capacitor C and L2 as part of the grid itself. With these assumptions, now inverter will resemble as an L-filtered inverter which is connected to an LC grid. With this, the capacitor connection point will become the PCC. Considering that inverter is controlled in a DQ frame, the block diagram of inverter along with its current control loop is shown in figure 2. Here PI is the PI controller. K is the combination of two components. One is a pulse width modulator gain and the other is digital time delay, which has to be taken into account when the control loop is implemented in digital platform. L1 is the inverter side inductor. Apart from that, here unity feedback system is considered just for simplicity. We have neglected the feedback sensor gains. So this is the inverter grid system taken for study. Now let us represent this inverter grid system using equivalent circuit representation as shown in figure 3. Here the inverter along with its filter element L1 are represented as a current source while the rest of the circuit elements remain same. Here we have two sources. If we consider the effect of one source at a time, let's say the effect of current source is considered. So if there is any harmonic component which causes the reactances of capacitor C and L2 to be equal, then definitely circuit will resonate and it leads to parallel resonance. And same thing holds good for voltage source as well. We are very much familiar with this kind of passive resonance in electrical engineering. The stability of the resonant circuit during resonance depends on the damping offered by the circuit. Now let us look into the more practical way of representing grid-tied inverter along with its current control loop. From figure 2, the output current expression can be written as shown at the bottom of the slide, where GC is the closed loop transfer function of the current control loop, IRF is the reference current of the control loop, Y0 is the closed loop output admittance of the inverter. Using this expression, grid-tied inverter, which was earlier represented as a current source in figure 3, can be rewritten as Norton's equivalent as shown in figure 4. We again now have two sources. If we consider the effect of one source at a time, right? So Y0 may interact with the rest of the circuit elements and effect is called as instability rather than calling it as resonance. Now let us identify the differences between figure 3 and figure 4. In figure 3, all the elements were passive, and hence damping offered by figure 3 will be either 0 or positive. Meanwhile, in figure 4, inverter output admittance Y0 is a function of control loop parameters plus passive elements of its filter elements. Therefore, Y0 is no more passive, but it will behave as an active admittance. So, apart from zero damping and positive damping, Y0 can also offer negative damping, so which is as good as amplification. Now, if at all Y0 interacts with rest of the impedances in negative damping region, system will lead to instability, and PCC quantities such as voltages and currents will get amplified, triggering inverter protection, and can even damage the power system equipments. Here, the expression of inverter output admittance is given. We can notice that Y0 is very much dependent on control loop bandwidth determined by the proportional controllers, and Y0 is also dependent on filter elements. In previous slides, we have seen how an inverter operating in grid connected mode interacts with grid impedance. Now, let us increase the complexity of the system and also see how such phenomena occur in islanded mode. Let us consider two inverters operating in islanded mode which are sharing a common load as shown in figure 5. Each inverter has a LC filter at its output terminal and they are operating in droop control mode. ZL1 and ZL2 are the line impedances connecting inverter 1 and 2 to the PCC. In figure 6, equivalent circuit of the system of figure 5 is shown. Inverters are represented using Thevenin's equivalent, that is, a voltage source in series with an equivalent output impedance of each inverter. Now let us neglect the voltage sources, and the remaining impedance network can be divided into two equivalent impedances. One is called the source impedance, the other is the load impedance. Here the closed loop output impedance of inverter 1, that is ZOV1, forms the source impedance, and the rest of the circuit forms the load impedance. Now let us plot source as well as load impedances versus frequency as shown in figure 7. One can notice that at 1.7 kHz, impedance intersection is observed, and at this intersection frequency, the phase margin is determined to be 0. So from control system point of view, system may go unstable or it may resonate depending on the damping offered by the inverter output impedance. It is also interesting to note that at intersection frequency, source impedance is capacitive while the load impedance is inductive. Apart from that, in the mid-frequency region, both source as well as load impedances, they are exhibiting RL impedance behavior, while in low frequency, they have somewhat RC impedance behavior. So this is the reason why harmonic instability is very much different from the resonance phenomenon that we see in normal passive circuits. Here, a comparison of electrical oscillations generated by the control system interactions in traditional synchronous generator and inverter fed renewable generation are shown in the first figure. The frequency points marked on the downward arrows are the bandwidths of the respective control loops of a typical synchronous generator and a typical grid-tied inverter system, respectively. In case of grid-tied inverter, control system may have outer and inner control loops. Outer control loops include AC as well as DC link voltage control, power control loops, and of course grid synchronization loops. And inner control loops in most of the cases will be a current control loop. Also, we are very much aware that innermost loops are the faster ones and the outer ones are slower. Therefore, inner loops are tuned for larger bandwidth while the outer loops are tuned for smaller bandwidths. The bandwidth of the control loop determines the frequency of dynamics generated by the control loop. Ultimately, the characteristics of these control loops in an inverter shapes the overall output impedance or admittance of the inverter. To be more precise, these control loops have larger impact on damping characteristics of inverter output impedance within their bandwidth range. As a result, outer loops may initiate harmonic instability or even resonance in low frequency region. Similarly, the inner loops in high frequency region. With this understanding, harmonic stability classification is shown in the second figure, which is purely based on a frequency of unstable oscillations resulting from impedance interaction. The first classification is the subsynchronous oscillation due to subsynchronous instability, and the second one is the one near synchronous oscillation. So these two can be together combined and called as low frequency oscillations or instability, because these oscillations are resulting from interactions initiated by outermost loops. Next classification is high frequency oscillations, which are initiated by the innermost loops. Nowadays, even oscillations near switching frequency are also studied in order to check the immunity of renewable fed power system. Anyways, we are not looking into that part. So, with this understanding, now we will consider a case study on how low frequency instability is witnessed in an inverter grid system due to grid synchronization control loops. Now, let us consider a case study on low frequency harmonic stability issues due to PLL, which is used for grid synchronization. Here, inverter with two different current control schemes are considered for study. One is decoupled DQ frame current control, which is designated as CC1 current controller 1. And the second one is alpha beta frame current control, which is designated as current controller 2, that is CC2. Both the current control schemes employ synchronous reference frame PLL for grid synchronization. But the impact that PLL has on the output impedance of inverter is different with respect to CC1 and CC2. Apart from that, since we are looking for a harmonic stability problem, I'm very much interested in finding whether PLL causes negative damping. If so, what is the frequency range that it offers negative damping? So we will answer all these questions in the subsequent slides. Since harmonic stability is very much dependent on external behavior of the inverter, that is the impedance or admittance of the inverter, we will develop impedance models, basically the small signal impedance models, and analyze the impedance characteristics of the inverter. Impedance models can be developed either in DQ frame or alpha beta frame. Here we have developed the models in DQ frame. So the current controller 2, which is in alpha beta frame, has to be frequency translated to DQ frame. To achieve this frequency translation, we have utilized convolution property of Laplace transform. Now, small signal impedance model can be obtained from the closed loop combined MIMO model shown in the figure for both CC1 and CC2. In this block diagram, the blocks in red as well as purple colors are the matrices which are resulting from PLL dynamics for both CC1 and CC2, while the blocks in black color are common for both the control schemes. Now we can derive a closed loop impedance for both CC1 and CC2 using this control block diagram. If we look at the resulting impedance model, it appears as a 2 cross 2 matrix shown at the bottom of the slide for both the current control schemes. So this matrix has 4 elements, out of which the diagonal elements are DD channel and QQ channel impedances, while the cross channel impedances are the off diagonal elements. These cross channel impedances are not affecting the stability. So we are not very much interested in looking into the impedance characteristics of these impedances. So we will look into the impedance characteristics of ZDD and ZQQ. Here, DD channel impedances are plotted with respect to frequency. Notice that in low frequency region, ZDD has a capacitive behavior. In high frequency region, it has inductive behavior. In between these two regions, resistive behavior is noticed. Therefore, DD channel impedance resembles an RLC circuit. Both CC1 and CC2 have same ZDD characteristics except for the resonant peak caused by resonant controller of CC2. We are very much interested to see the QQ channel impedance characteristics of CC1 and CC2 because PLL regulates Q axis voltage so that dynamics of PLL affects ZQQ. In figure B, QQ channel impedance characteristics of CC1 is plotted for different PLL bandwidth, while in figure C, it is the plot for CC2 for different PLL bandwidths. ZQQ of both CC1 and CC2 are exhibiting negative damping in low frequency region. And also notice that negative damping is a function of PLL bandwidth. For CC1, negative damping range increases with the increase in PLL bandwidth, while that of CC2, it is not very much significant. I mean to say, it is not very much dependent on PLL bandwidth. And for all the three PLL bandwidths, damping region is same for CC2. Due to this difference in negative damping region, CC1 and CC2 have different interaction profiles with the grid impedance, which will be discussed in future slides. As a result, D axis and Q axis loses the symmetry, and hence we obtain impedance models in matrix form. So far, we have seen how PLL in CC1 and CC2 is exhibiting negative damping on QQ channel impedance. It is also observed that it is a function of PLL bandwidth. But from previous frequency response analysis, it is very difficult to identify how negative damping of PLL in QQ channel impedance affect the overall output impedance of the inverter. Also, it is very much difficult to predict interactions among inverter output impedance and grid impedance due to PLL. To overcome this drawback, the impedance model, which is in 2 cross 2 matrix form, will be transformed into two eigenvalues using generalized Nyquist criteria, which is a control system analysis tool for linearized system. Now these eigenvalues are plotted with respect to frequency along with grid admittance. If any one of the eigenvalues intersect with the grid admittance, as shown in figures A and B, then phase margin at the intersection frequency determines the occurrence of instability of or resonance. Now let us look into the impedance interaction scenarios in case of CC1 due to PLL. In figure A, where PLL bandwidth is 42 Hz, interactions are happening at 297 Hz. Since there is sufficient phase margin, system is stable. But in figure 2, where PLL is tuned for 165 Hz bandwidth, interaction is witnessed at 283 Hz, but the system is unstable due to poor phase margin, which is less than 0. Notice here that the interaction frequency, that is 283 Hz in figure B, falls into negative damping region of QQ channel impedance of CC1. For current controller 2, at 165 Hz PLL bandwidth, there is sufficient phase margin and the system is stable. But for CC1, instability is witnessed for same PLL bandwidth. This difference in interactions with grid impedance is due to dissimilar negative damping offered by PLL. In this part of the presentation, we will look into the average model simulation results and experimental validation of analytical findings. First, we will validate for CC1. Here in figure A, initially inverter is operating with a PLL tuned to 42 Hz bandwidth, and system is found to be stable without any interactions. At 0.85 seconds, PLL bandwidth is changed to 165 Hz, and the system is witnessing unstable oscillations at PCC due to interactions among inverter and grid impedance. From previous analysis, we have seen that interaction frequency is found to be 283 Hz. In the FFT plot shown at the right side of figure A, basically this is the FFT plot of inverter output current. we can notice that an interharmonic at 276 Hz is being amplified, which is close to 283 Hz determined from the analysis. Also, there is one more component at 176 Hz. These two components are 100 Hz apart, that is twice the grid fundamental frequency, hence they are called frequency coupled harmonics. Notice that interaction is happening somewhere close to 276 Hz. But there is one more harmonics generated at 176 Hz, which are called frequency coupled harmonics. And these kind of harmonics are very much common in PLL based control systems. Apart from that, notice here that the reference current for inverter is 20 amps for both the PLL bandwidth case. Now we will see how negative damping region is a function of reference current. In figure B, initially PLL bandwidth is maintained at 165 Hz, while the reference current is kept constant at 20 amps. At zero point 0.9 seconds, reference current is changed to 15 amps and system is still unstable. And also notice from the FFT plot of inverter output current that the frequency coupled harmonics have shifted right with respect to frequency axis. I mean to say interaction is happening at somewhere close to 310 Hz. Later at 0.96 seconds, reference current is changed from 15 amps to 10 amps and now the system enters the stable state. In the sense, no more negative damping in this frequency range is observed. In summary, harmonic instability caused by negative damping is dependent on operating conditions of the system such as power reference to the inverter, presence of parallel inverters, and even it depends on grid strength. This is the experimental setup used to validate the analysis. Control system is implemented in FPGA platform. Looking into the waveforms obtained from the experiment, for 45 Hz PLL bandwidth with current controller 1, system is found to be stable. The corresponding A phase PCC voltage and current along with the frequency spectrum of inverter output current are shown. Since system is stable, the frequency spectrum has only the 50 Hz component. At 165 Hz PLL bandwidth and 20 amps reference current, system is unstable and coupled harmonics being injected to the grid are also captured. With same bandwidth, reference current is now changed to 15 amps. The system remains unstable and one can also notice frequency shift in the coupled harmonics and also reduction in their magnitude. For CC2, as we have seen in frequency domain analysis, system is stable even at 165 Hz PLL bandwidth. This is because of the insignificant negative damping offered by PLL in CC2. These are some of the conclusions drawn from this case study. Even though PLL is present in both CC1 and CC2 for grid synchronization, negative damping region is not identical. As a result, low frequency interaction profiles of the inverter with CC1 and CC2 are different. We have also seen how negative damping is a function of operating condition, especially the reference current. We have also noticed system switching from stable state to unstable state and vice versa due to change in the damping characteristics of the inverter control system. And lastly, we conclude saying that at higher PLL bandwidth, CC1 has high probability of interacting with grid impedance compared to CC2. If so, then what is the necessity of going for higher PLL bandwidths? Answer is that when grid is distorted, keeping PLL bandwidth below 50 Hz improves PLL performance. But this will affect low voltage right through operations, which require higher PLL bandwidth for fast detection of grid voltage phase angle. As a result, choice of PLL bandwidth is always a trade-off between these two conditions. That's why PLL bandwidth beyond 50 Hz are considered for analysis. So far, we have seen how inverter grid system undergoes low frequency interactions due to PLA. Currently, we are working on interactions between any two inverters in a multi-parallel inverter system. When two inverters interact, there can be resonant circulating current flowing between them. Also, these two inverters may interact with grid in high frequency region due to current control or damping. So all these things will be addressed here. Later, a SIGRE benchmark of a European low voltage distribution system where 5 inverters are connected at different buses will be considered. Here, line to line voltage is 400 volts RMS, and this LV network is connected to medium voltage line through 400 kVA transformer. For this system, we will analyze the currents of harmonic instability by considering different case studies. Thank you.